Welcome back. This will be the solution to number 3 on the optimization practice worksheet. If 5,000 square feet of material is available to make a box with a square base, find the largest possible volume of the box. And then just for clarity here, it says assume the box has 4 sides, a top and a bottom. Very often you see a similar problem to this, but it doesn't have a top. It barely changes the work. It actually doesn't increase the difficulty at all, but it just needs to be really clearly stated in the problem. So this is number 3 on the worksheet. And if we peek up at number 2, you may notice that this is kind of the 3-dimensional version of the question posed in number 2. So it'll have all the same steps, just be a little bit messier in every phase, but that's okay. Okay, so I have already drawn a very spectacular 3D box here. They're telling me that the box has a square base. So we know there's 3 dimensions to measure here. You have your length, your width, and your height. And if they say the base is a square, they mean a perfect square. So like this distance and this distance are the same letter. So I'm going to use X for that dimension. And then the height of this box can be anything. So I'm going to make a second letter. I'll use Y just as my default, but you could use H for height, just the same. Okay, so we drew our picture and labeled what we could. And now we want to decide what is the objective function? What's the quantity that actually needs to be maximized or minimized? They're saying the largest possible volume. So that tells me that volume is my objective function. We want to maximize volume. The other information, specifically the 5,000 square feet of material, that's the constraint, right? That's like the fixed value of something. That's just going to help us in the step where we make volume a function of a single letter. All right, so in this picture, the volume is length, width times height. So that'll be X times Y. So I'm going to say V equals X squared times Y. Okay, so this is just like the previous 2. This starts out as a function with 2 inputs. We're going to use our constraint to make it a function of a single input. So we have 5,000 square feet of material. Technically, that's surface area, but you don't need to remember a fancy surface area formula. We can just kind of add up the areas of all 6 sides here. So 5,000. So it's going to be the area of the base of the box plus the top. Those will be the same area. And then plus 4 times the area of a side. All 4 sides have the same area. All right, so the base is X times X, that's its area, so it's X squared. And then the top is also X times X. So I'll say X squared, but instead of adding them together, I'll say 2X squared for the base and the top. Each side has a width of X and a height of Y. So that's plus 4X. All right, so this constraint formula is a lot messier than the previous ones that we've seen. This is one of the ones where it's much easier to solve it for one of the letters than the other. So solving this for X is really tricky because X is here and here, you have a quadratic. It's possible, but it's really messy. Solving this for Y, because Y is only right here, is much easier to do. So that's definitely what we should do here to make the rest of the problem as clean as possible. So I'll solve this for Y. Subtract 2X squared. And then divide by 4X. And I get that Y is 5,000 minus 2X squared over 4X. You can leave it in this form. It's not really going to get pretty. One thing you might notice is that all 3 of these terms could be divided by 2. So let's go one more step. And we'll say Y equals 2,500. So that's 5,000 divided by 2 minus X squared over 2X. So that's going to be my constraint. And that's what I'm going to plug in for X, right? Or sorry, for Y in this formula here. And like I said, it'll be messier than everything we've done so far, but the steps are the same, so we'll just be careful. All right, so volume as a function of just x, we have x squared times, and instead of y, I'm going to put all of this. 2,500 minus x squared over 2x. All right, so we have a function. We need to find the location of its maximum value, its global maximum specifically. That always starts by finding the critical numbers, so we need to compute the derivative. I want to simplify this as much as possible before I start taking the derivative because it's so yucky looking. So one thing to notice here is that this x squared and this x down here, there's some cancellation. So we have x, and then this over 2 is like a times a half. Times 2,500 minus x squared. I'm just going to clean this up as much as I can. So that's 1/2 x times 2,500 minus x squared. And then I'll distribute the 1/2 x in. Again, I'm just kind of trying stuff to make this look as nice as possible. All right, so that's 2,500 over 2. I'm going to leave it that way because I don't have a calculator, but you can simplify that if you want. Times x minus 1/2. So we have an x here and an x squared, so that gives me x cubed. All right, so that's roughly as good as I can get my volume formula. So now I'm going to take the derivative. 2,500 over 2, that's 1,250. All right, so v prime is that 1,250 number minus 1/2 times 3x squared. And the only thing we can really clean up is 1/2 times 3 is 3 over 2. And we're gonna set this equal to 0. There's no domain restrictions here, so we're just gonna get the normal kind of critical number. Right, and I'm gonna solve for x. I'm gonna add 3/2 x squared onto the left. I want to divide both sides by 3/2, which is the same as times 2/3. So 1,250 times 2 brings us back to 2,500. So I'll have 2,500 over 3. It's not a particularly nice number, I don't think. And now I'm going to plus or minus square root both sides. And my critical numbers are the plus or minus square root of 2,500 over 3. You can certainly simplify that because 2,500 is a perfect square, but the 3 is not, so I'm actually just going to leave it here. Okay, so a couple of things to notice before we check our critical numbers. One is that we can toss, we have 2 critical numbers, but we can disregard the negative one because x is supposed to be a side length, right? So it doesn't make sense for any negative values of x. So I'm going to check this again using the first derivative test, and I'm just going to kind of cut my number line at 0 and mark the one relevant critical number. As long as there's only one relevant critical number, the first derivative test is going to work just fine here. So I have the square root of 2,500 over 3. And I don't have a calculator, so I'm going to do my best to check the numbers that I can here. V prime, I'm going to look probably at this format, 1,250 minus 3/2 x squared. All right, so I just need to figure out if the output would be positive or negative. So something between 0 and this number. This number is bigger than 1 because 2,500 is so big. So let's say 1. If I plug a 1 in right here, I get 1,250 minus 3/2. That's definitely positive. Okay. And then a number bigger than root 2,500 over 3, 1 million, right? That's a safe choice. If I plug in 1 million for x right here, I get 1,250 minus 3/2, 1 million squared. This part is huge, right? Because it has a million squared in it. So 1250 minus that number is definitely negative. There's a truck driving past my house right now. I don't know if you can hear it. All right, so this shows me that within the relevant domain, my derivative goes positive to negative, which means the function for volume goes up and then down. So we must have a maximum right here, which does agree with what we were looking for. So this guy is the location of our answer. And we just want to go back and make sure we answer the question that was actually asked. So we're going to put units on it and then interpret as best we can. So the question specifically said, find the largest possible volume. So we're not going to give our answer as dimensions. We're going to actually compute the volume of this box when that is the value of X. So I'm not going to go back and find Y. I could do that. So I could find the matching Y and then plug those values in here. Or I could take this value of X and plug it into my volume formula, which is any one of these three forms. Either way will give you the same answer. They're both just as good. So we'll say when X equals the square root of 2500 over 3, your volume is, I'm going to use, not sure which of these is going to come up the prettiest. Why don't we use this last form here? So I would have 2500 over 2, which is the same as 1250, but I'll leave it, times X. This is what I'm plugging in for X, minus 1/2 times what I'm plugging in for X. Because I don't have a calculator in theory on this worksheet, I'm going to leave the number this way and say, if you want a real number, plug this into a calculator, and I'll just put some units on it. So we had feet as our units, and this is volume. So this would be in cubic feet, which is feet cubed. That's my answer. If you are curious and you throw this into a calculator, it should come out to about 24,056.26 cubic feet.